Hello calculus fans, welcome back. Today we're going to be looking at assignment 14, section 4.2, which is all about implicit differentiation. And this technique of differentiation will enable us to complete taking the derivatives of the remaining elementary functions. So it's very powerful. So let's consider the following. Not all relations can be expressed in the form y equals something in terms of x. Sometimes you'll have a smooth curve, a relation, which, because it's smooth, is differentiable, but it can't be solved for y, or it can't be solved for y easily. Here's an example of one. X cubed plus y cubed minus 9 times x times y is equal to 0. This is a pretty curve, and I'll show you to you in a second. But if you notice, it would not be a very easy task to solve this for y explicitly in terms of x. So I've included the graph of this relation, and notice that it is a relation and not a function. And also notice that as we trace around it, it's smooth. There are no corners, there are no cusps. There may be some places where the derivative is undefined, but it's essentially a smooth curve, and so therefore it makes sense that dy dx should exist. So to help us understand implicit differentiation, let's look at a couple of these examples that I have outlined. First couple are very clear. We know that the derivative of x cubed is 3x squared. We know the derivative of x squared is 2x, and we know the derivative of x is 1. Now, to notice is the variable here and the variable here are the same. When we take the derivative of, say, of x with respect to x, well, we're just looking for the slope of the tangent line to the graph of y equals x. And we know that everywhere that slope is equal to 1. But think about what happens when I want to take the derivative with respect to x of y. We have no idea what y equals. Y might be x squared, y might be e to the x, y might be sine x. We don't know, and so the best we can do is simply write this as dy dx. So now let's look over here on the right side, and here we have an example that helps us understand how implicit differentiation works. We're taking the derivative with respect to x of y squared. So this is a direct application of the chain rule. And really we have a function y, which we know nothing about. That's the inner function. And the outer function is something squared. And so we have seen that the derivative of this is 2y dy dx. And that dy dx here at the end is the whole thing. That's the derivative of the inside function. And similarly, the derivative here is 5y to the fourth dy dx. And that is the heart of implicit differentiation. Not very difficult, just remembering that you have to take the derivative at the end of the thing inside. So let's look at some more examples. Suppose we're taking the derivative with respect to x of the sine of y. Well, using the chain rule, we know that that's going to be the derivative of the outside function. Leave the inside alone, and then you take the derivative of the inside function. And the best I can do with taking the derivative of y with respect to x is write it as dy dx. So now let's suppose we have a relation that looks like this. We have x squared y cubed is equal to 5. And we want to find dy dx. So what we'll do here is differentiate each side with respect to x. That looks like this. the derivative with respect to x of x squared times y cubed is equal to the derivative with respect to x of 5. Now in the first case, because it's a product, we need to use the product rule. And so we have the first times the derivative of the second plus the derivative of the first times the second, and that equals the derivative with respect to x of 5, which we know to be 0. If I now solve for dy dx, I'm going to get minus 2xy cubed divided by 3x squared y squared. Kind of messy, but that's the derivative. At this point in the understanding of implicit differentiation, I think it's helpful to go back and say, okay, we know now that the derivative with respect to x of y squared, using the chain rule, is 2 times y times the derivative of the innermost function. Well, shouldn't the same thing work with the derivative with respect to x of x squared? And indeed it does. Let me show you. That's going to be 2 times x, and if I do the same thing, it's the derivative with respect to x of x. But since the derivative with respect to x of x is 1, we simply get 2x. But it's helpful to see that we can do exactly the same thing in each case. In the second case, things simplify because we're taking the derivative of x with respect to x. So let's take a look at this example. Here we're asked to find the equation of the tangent line to the relation x squared plus y squared equals 25 at the point minus 3, 4. So please notice that x squared plus y squared equals 25 is a circle centered at the origin with radius 5. And it's a smooth and differentiable curve, so it will have a tangent line at all points. So we take the derivative of each side with respect to x, and we get 2x plus 2y times dy dx is equal to 0. Now rather than solve for dy dx here, which I could do, a lot of times in questions like this, it's much easier to just put in the values for x and y and then solve for dy dx. It's not so easy here. It's not such a difference here. But there are problems in which it's much better to put in the point first and then solve for dy dx. At any rate, if I do that, I get minus 6 plus 8 dy dx equals 0. So dy dx at the point minus 3, 4, it's important to see that kind of notation, is equal to 3/4. And therefore the equation of the tangent line, we use point slope form, is y minus 4 is equal to 3/4 times x plus 3. And that's the flavor of that kind of question. So now let's talk about the power rule. And what we're going to be able to do now is extend it to rational exponents. Recall that we have already shown that the derivative with respect to x of x to the k is k times x to the k minus 1. And that's where k is any integer at all. So now let's suppose that we're looking at the derivative with respect to x of x to the p over q. And this is where p and q are integers and q not equal to 0. So if we can show what this is, then we'll have extended the power rule to rational exponents. So let's see if we have room for this. We write y is equal to x to the p over q. We raise each side to the q power, so we get y to the q is equal to x to the p. Now we differentiate with respect to x, and we get q times y to the q minus 1 times dy dx, I'll cheat and write it as y prime, equals p times x to the p minus 1. So therefore y prime is equal to p times x to the p minus 1 over q times y to the q minus 1. But remember now that y is equal to x to the p over q. So I'll make that substitution. I'll write this as p over q times x to the p minus 1 over x to the p over q raised to the q minus 1. And I can write that as p over q times x to the p minus 1 over x to the p minus p over q. Trust me on that. So here's where we are. And now if I subtract exponents, we get that the derivative with respect to x of x to the p over q will be p over q times x to the p over q minus 1. So in other words, the power rule is extended now for all rational exponents. So as a final example, let's look at the derivative with respect to x of the square root of x, which we can write as the derivative with respect to x of x to the 1/2, which we know now is 1/2 times x to the minus 1/2, which we can write as 1 over 2 times the square root of x. And that's it for implicit differentiation. When we meet next, we'll learn how to use implicit differentiation to take derivatives of the remaining elementary functions. See you then.